အားလုံးမင်္ဂလာပါဒီနေ့ကလည်းဆိုတော့ဒီ linear algebra ကိုဆက်လေ့လာနေပေါ့ဆက်လေ့လာနော်အော် linear algebra ဆိုလို့ LS ကိုလိုင်းကလည်းဒီခဏရနော် information တစ်ချက်ပြောချင်တော့ဒီဟာလေးကို LS ကဒီတင်ချာနဲ့ပတ်သက်ပြီးပေါ့နော် LS collaboration တစ်ခုလုပ်ဖို့အစီအစဉ်ဆွဲနေပါတယ်လို့နော်ဒီဘာနဲ့ပတ်သက်ပြီးဘယ် page ကို collaboration လုပ်ဖို့အစီအစဉ်ရှိလဲဆိုတော့လေဒီဟာလေးကိုဒီတင်ချာယူပတင်ချာဆိုရဟာလေသိထားမိကြလားဒီဟာလေးလေဒီ page ကိုသိထားမိကြလားဒီ page မှာဒီ page ကလူနဲ့ LS နဲ့ collaboration တစ်ခုလုပ်ပြီးတော့တင်ချာနဲ့ပတ်သက်တဲ့ဟာလေးအရေးပါတဲ့ဟာလေးဆိုလုပ်ဖို့တစ်ခုအစီအစဉ်ဆွဲနေပေါ့နော်လို့ဆိုတော့တဖြည်းဖြည်းနဲ့လက်ခံပေးပါလို့လက်ခံတဖြည်းနဲ့စောက်ပေးပါပေါ့နော်ဒီဟာလေးနဲ့ဒီနဲ့ collaborate လုပ်ဖို့စကားပြောနေပေါ့နော်တကယ်လို့အဆင်ပြေတယ်ဆိုရင်တင်ချာနဲ့ပတ်သက်တာလည်း clay တွေကိုအုံနောက်လေးရောက်စေချင်တာလည်းပါတယ်ပေါ့နော်ဒီမှာဆိုရင်သူတော်များမျက်စိနဲ့မြင်တာထင်တော်များပြောတာရှိသူဟာလေးလည်းဒီ page ကိုလည်း follow like လုပ်ထားကြပါပေါ့နော်တော်တော်လေးအဆင်ပြေတယ်လို့နော်ဒါလေးတစ်ချက်ပြောဖို့အဲ့တော့ဘူပါနဲ့တင်ချာကိုလည်းမရမရကတနည်းမဟုတ်တနည်းတော့ရအောင်လိုက်ရမှာပဲဟုတ်တယ်ဟုတ်ကိုမနိုင်တော့နိုင်တဲ့လူကို share ခေါ်ပြီးဆရာတင်လို့လိုက်မှာပဲဟုတ်တယ်ဟုတ်လို့ဆိုတော့ don't give up okay you can do it အဲ့လိုဆိုတော့ဒါလေးတစ်ချက်ပေါ့နော်လက်စအကြောင်းကြားခြင်းနဲ့ကလေးအားလုံးเนาะအဲ့လိုဆိုတော့ don't worry about it we will try to go step by step เนาะအဲ့လိုဆိုတော့မနေ့ကအဲ့လိုဆိုရင် metric နဲ့ဒီ scalar နဲ့ transform ဘယ်လိုလုပ်လဲဆိုရဟာလေးလို့ဆိုတာကြည့်ထားတယ်ပေါ့နော်အဲ့လိုဆိုတော့ဒီနေ့က metric transformation ပို့ပြီးတော့သေးသေးတခြားလေးပေါ့နော်ခုန scalar နဲ့လုပ်ပါတာဒီက function နဲ့ပါတယ်နဲ့လုပ်မှာဆိုတော့အဲ့လက်ဆက်ဟာ connection slow ဖြစ်နေ။ Okay ဒီနေ့ကတော့ဆိုဒီရောက်နေပေါ့နော်။မနေ့ကအဲ့ဒါပြီးသွားပြီဆိုတော့ဒီဟာဒီပြီးသွားပြီ။အဲ့လိုဆိုတော့လဲဆိုရင်ဒီကကျ functional linear algebra အဲ့လိုဆိုပြီးသွားပြီဆိုတော့မှရှိရနော်။အဲ့လိုဆိုတော့လဲဆိုပြီးသွားမလဲဆိုတော့ဒီနေ့ကကြတော့ဒီ linear transformation တွေသွားမယ်ဒီဟာလေးတွေပေါ့နော်ဒီဟာလေးနည်းနည်းအရေးကြီးတဲ့ပုံစံပေါက်တယ်ပေါ့နော်လက်မရှိတယ်မှာလို့ဆိုတော့လဲဒါလေးတစ်ချက်ကြည့်အောင်ဒီ metric နဲ့ multiplication metric က very very important ပေါ့နော်မနေ့ကလည်း programming assignment explain လုပ်တော့လည်းပြောပြတယ်ပေါ့နော်အရင်ရေးပါတဲ့ပုံအဲ့လိုဆိုတော့ machine learning တို့ AI တို့ကသူကဒီ number တွေကိုပဲတွားပြီးတော့တွားလုပ်နေရလေအဲ့လိုဆိုတော့ဒီဟာနဲ့ပတ်သက်ပြီးသိကိုသိရမယ်ပေါ့နော်လို့ဆိုတော့လဲဆိုတော့ဒီချိန်မှာကိုကောင်းစားနေတောင်မှကောင်းစားခံပေါ့နော်အဲ့ဒါလေးတစ်ချက်ပြောချင်တယ်နော်ဟုတ်ပြီဖတ်ကြည့်အောင်နော်ဒါလေး
We've talked a lot about linear transformations. What I want to do in this video, and actually the next few videos, is to show you how to essentially design linear transformations to do things to vectors that you want them to do. So we already know that if I have some linear transformation T, and it's a mapping from Rn to Rm, then we can represent T, what T does to any vector in X, or the mapping of T of X in Rn to Rm, we can represent it as some matrix times the vector X, where this would be an m by n matrix. M by n matrix. And we know that we can always construct this matrix, that any linear operation, any linear transformation can be represented by a matrix this way, and we can represent it by taking our identity matrix, you've seen that before, by taking the identity matrix with n rows and n columns. So it literally just looks like this. So it's a 1, and then it has n minus 1 zeros all the way down, then it's a 0, 1, and then everything else is zeros all the way down. And so essentially you just have ones down as diagonal. It's an n by n matrix. All of these are zeros, just like that. You take your identity matrix and you perform the transformation on each of its columns. On each of its columns. And we call each of these columns the standard basis for Rn. So this is column E1, this is column E2, and it has n columns, En. And each of these columns are, of course, members of Rn, because this is an n rows and n column matrix. And we know that A, our matrix A, can be represented as the transformation being operated on each of these columns. So the transformation on E1, the transformation on E2, so forth, and so on, all the way to the transformation En. And this is a really useful thing to know, because it's very easy to operate any transformation on each of these basis vectors that only have a 1 kind of in its corresponding dimension, or with respect to the corresponding variable, and everything else is 0. So let's, all of this is review. Let's actually use this information to construct some interesting transformations. So let's start with some set in Rn. And actually everything I'm going to do is going to be in R2, but you can extend a lot of this into just general dimensions. But we're dealing with R2 right here. Obviously, it's only 2 dimensions right here. Let's say we have a triangle formed by the points. Let's say the first point is right here. Let's say it's the point 3, 2, 3, 2, and then you have the point. Let's say that your next point in your triangle is the point, well, let's just make it the point minus 3, 2. I shouldn't have written that as a fraction. I don't know why I did that. 3, 2. Then you have the point minus 3, 2. And that's this point right here, minus 3, 2. And then let's say, just for fun, let's say you have the point, let's say we have the point, or the vector, the position vector, right? 3, minus 2. 3, minus 2, which is right here. Now each of these are position vectors, and I can draw them. I could draw this 3, 2 as in the standard position by kind of drawing an arrow like that. I could do the minus 3, 2 in its standard position like that. And 3, minus 2 I could draw like that. But more than the actual position vectors, I'm more concerned with the positions that they specify. And we know that if we take the set of all of the positions, or all of the position vectors that specify the triangle that essentially formed by connecting these dots, the transformation of this set, so we're going to apply some transformation of that, is essentially you take the transformation of each of these endpoints and then you connect the dots in the same order. And we saw that several videos ago. But let's actually design a transformation here. So let's say we want to, let's just write down in words what we want to do with our whatever we start in our domain. Let's say we want to reflect around the x-axis, reflect around the, well, actually let's reflect around the y-axis, So we essentially want to flip it over. We want to flip it over that way, so I'm kind of envisioning something that'll look something like that when we flip it over. So we're going to reflect it around the y-axis, and let's say we want to stretch in y direction by 2, in y direction times 2. So what I envision, we're going to flip it over like this, what I just drew here, and then we want to stretch it. So we're going to first flip it, that's kind of step 1, and then step 2 is we're going to stretch it. So instead of looking like this, it'll be twice as tall, so it'll look like this, without necessarily stretching the x. So how can we do that? So the first idea of reflecting around the y-axis, right? So what we want is this point that was a minus 3 and the x-coordinate right there. We want this point to have its same y-coordinate. We want it to still have a 2 there. And I'm calling the second coordinate here our y-coordinate. I could call that our x2 coordinate, but we're used to dealing with the y-coordinate when we graph things. So I'll just keep calling it the y-coordinate. What we want is this negative 3 to turn to a positive 3. And because we want this point to end up over here. And we want this positive 3 here to end up becoming a negative 3 over here. And we want this positive 3 for the x-coordinate to end up as a negative 3 over there. So as you can imagine, all we're doing is we're flipping the sign. When this reflection around y, this is just equivalent to flipping the sign of the x-coordinate. So this statement right here is equivalent to minus 1 times the x-coordinate. So let me call that, or let's call that times x1, because this is x1, and then stretching in the y direction. So what does that mean? That means that whatever height we have here, so this next step here is whatever height we have here, I want it to be 2 times as much. So right here, this coordinate is 3, 2. If I didn't do this first step first, I would want to make it 3, 4. I want to make it 2 times the y-coordinate. So the next thing I want to do is I want to do 2 times, well, I could either call it, well, let me just call it the y-coordinate. It's a little bit different convention than I've been using, but I'm just calling these vectors. Instead of calling them x1 and x2, I'm saying that my vectors in R2, the first term I'm calling the x term or the x entry, and the second term I'm calling the y entry. But it's the same idea that we've been doing before. I'm just switching to this notation because we're used to thinking of this as the y-axis as opposed to the x1 and the x2 axis. So how do we construct this transformation? I mean, I can write it down in kind of transformation words. I could say, I could define my transformation as T of some vector x, or let me write it this way, T of some vector xy is going to be equal to, I want to take minus 1 times the x, so I'm going to minus the x, and I'm going to multiply 2 times the y. So that's how I could just write it in transformation language, and that's pretty straightforward. But how would I actually construct a matrix for this? So what you do is you just take we're dealing in R2, so you start off with the identity matrix in R2, which is just 1, 0, 0, 1, and you apply this transformation to each of the columns of this identity matrix, to each of the columns of that identity matrix. So if you apply this, if you apply the transformation to this first column, what do you get? So what we're going to do is we're going to create a new matrix A and say that is equal to the transformation of, let me write it like this, transformation of 1, 0. That's going to be our new column. We're just going to transform this column. And then the second column is going to be the transformation of that column. So it's transformation of 0, 1, just like that. So what are these equal to? The transformation of 1, 0. So let me write it down here, green. So A is equal to, what's the transformation of 1, 0, where x is 1? Well, we just take the minus of the x term, so we get minus 1, and then 2 times the y term, so 2 times 0 is just 0. Now do the second term. The minus of the 0 term is just minus 0, so that just stays 0. And you multiply 2 times the y term. So 2 times y is going to be equal to 2 times 1, so it's equal to 2. So now we can describe this transformation. So now we can say the transformation of some vector x, y, we can describe it as a matrix vector product. It is equal to minus 1, 0, 0, 2 times our vector, times x, y. And let's apply it to verify that it works, to verify that our matrix works. So this first point, and I'll try to do it color-coded, let's do this first point right here. This is minus 3, 2. So that's minus 3, 2. So what is minus 3, 2? I'll do it right over here. I can just look at that. So what is minus 1, 0, 0, 2 times minus 3, 2? Well, this is just a straight up matrix vector product. Minus 1 times minus 3 is positive 3, plus 0 times 2, so plus 0. So this is 3. And then 0 times minus 3 is 0, plus 2 times 2, so it's 3, 4. So that point right there will now become the point 3, 4. It now becomes that point right there. Let's look at this point right here, the point 3, 2. So let's take our transformation matrix, minus 1, 0, 0, 2 times 3, 2. This is equal to minus 1 times 3 is minus 3 plus 0 times 2. So it's just minus 3. You have 0 times 3, which is 0, plus 2 times 2, which is 4. 0 plus, so you get that point. So this point, by our transformation t, becomes minus 3, 4. So minus 3, 4. And I kind of switch in my terminology. I say it becomes, or you could say it's mapped to, if you want to be kind of use the language that I use when I introduce the ideas of functions and transformation. This point is mapped to this point in R2. And then finally, let's look at this point right here. Apply our transformation matrix that we've engineered. Let's multiply minus 1, 0, 0, 2 times this point right here, which is 3 minus 2. 3 minus 2, which is equal to minus 1 times 3 is minus 3, and then 0 times minus 2 is just 0, so this becomes minus 3, and then 0 times 3 is 0, 2 times minus 2 is minus 4, so minus 3, minus 4. So this point right here becomes minus 3, minus 4, becomes that point right there. And we know that the set in R2 that connects these dots by the same transformation will be mapped to the set in R3 that connects these dots. We've seen that already. I think that was 3 videos ago. So the image of this set that I've drawn here, this triangle is just a set of points specified by a set of vectors. The image of that set of position vectors specifies these points right here. Specifies the points that I'm drawing right here. Let me see if I'm doing it right. There you go, just like that. And lo and behold, it has done what we wanted to do. We flipped it over so that we got kind of this side onto the other side like that, and then we stretched it. And we stretched it in the y direction, and we see that it has stretched by a factor of 2. We flipped it first, and then we stretched it by a factor of 2. And in general, any of these operations can be performed. I mean, you can always go back to the basics. You can always say, look, I can write my transformation in this type of form, then I can just apply that to my basis vectors or the columns in my identity matrix. But a general theme is any of these transformations that literally just scale in either the x or y direction, and when or essentially just, well, you could say scale, they can either shrink or expand in the x or y direction, or flip in the x or y direction, creating a reflection. These are going to be diagonal matrices. Diagonal matrices. And why are they diagonal matrices? Because they only have non-zero terms along their diagonal. This is the 2 by 2 case. If I did a 3 by 3, it would be zeros everywhere except along the diagonal. And it makes a lot of sense because this first term is essentially what you're doing to the x1 term. The second term is what you're doing to the x2 term. If you had, or the y term in our example, if I had multiple terms, if this was a 3 by 3, that would be what I would do to the third dimension. Then the next term would be what I would do to the fourth dimension. So you could expand this idea to an arbitrary Rn. But anyway, this whole point of this video is to kind of introduce you to this idea of creating custom transformations. And I think you're already starting to realize this could be very useful if you want to do, especially in computer programming, if you're going to do some graphics or create some multi-dimensional games.
ဟုတ်ပါပြီဒါလေးကိုတူတူကြည့်နေရလို့လည်းရှိတယ်ပေါ့နော် electron နဲ့တူတူကြည့်နေရလို့လည်းရှိတယ်ဒီဟာလည်းအရင်သဘောကျတယ်ဒီဟာလေးကိုကြည့်နေတာလေဒီဟာလေး electron ဒီ OpenCV course မှာလည်းလုံးဝအခုလောဆယ်သင်နေတဲ့ဟာလေးနည်းနည်းပေါ့နော်ပြန်ပြီးတော့ချိတ်ဆက်လို့ရမယ်ထင်တယ် image တွေကိုလေဒီမျိုးစလုပ်လိုက်တာပါလေလား just split လုပ်တာတို့အဲ့လိုမျိုးလုပ်တဲ့ဟာလေးဒီနော်ဒီဟာနဲ့ပတ်သက်ပြီး question လေးရှိရအမှန်ဆိုဒီဟာလေး identity unit တွေပါရမှာလို့သိမှာပါဒီမှာဘာလို့ -1 ဖြစ်ရလဲ2ဆိုတာဒီဟာကိုကြည့်ပြီးတော့ပေါ့နော်လုပ်လိုက်လေဆိုတဲ့ဘောလေး identity နဲ့ဒီကိုပေါင်းလိုက်လေဆိုတဲ့ဘောလေးပဲပေါ့နော်ဒါလေးတစ်ချက်ပေါ့ရတူတွက်တာတန်းရိုးဆိုတွက်နေရတာထပ်တွက်နေဖြစ်ရလာမှာပါအဓိကဒီမှာအဓိကကြည့်ရမှာပါလဲဆိုတော့ scale လုပ်ချင်ဘယ်လိုလုပ်လဲပေါ့နော်ဒီ reflection ဘယ်လို stretch လုပ်ချင်ဘယ်လိုလုပ်လဲကို image ကကွာ2က2ရှိတယ်ဘာလို့လဲဆိုတော့200နဲ့200ရှိတာကွာဟာ200မဟုတ်ငါ400လို့ရှင်အဲ့လိုမျိုးဘယ်လို stretch လုပ်လဲဆိုပြီး operation ကဘယ်လိုလုပ်သွားလဲဆိုတော့နည်းစီမြင်လာတယ်ဒီနေ့ပတ်သက်ပြီး question လေးရှိလာ Alex ကိုဘယ်လိုမြင်လဲနည်းနည်းခက်လားနားမလည်ရသေးရှင်လုပ်ပါအောင် Alex trying to explain လုပ်ပေးနေပေါ့နော်နားလည်သလိုအဆင်ပြေကြလား hello အတန်လေးလုပ်ကြမယ်ဟောအတန်လေးမလုပ်ကြမနေကြတယ်ဟောအဆင်ပြေကြလားအဆင်ပြေဟောမပြင်ဘူးဒီနေ့ပါတန်လေးလုပ်ပါလို့ပြရတယ်ဟုတ်ကဲ့ပါအဲ့လိုဆိုတခြားလူတွေရောအဆင်ပြေညီမလေးရင်ထူလို့ပါတော့ကိုယ့်ကိုကြည့်နေတဲ့လူတွေအဆင်ပြေလားအဆင်ပြေ
ဟုတ်ကြည့်ပါတေချာတော့အသေးလေးတော့ပြန်ကြည့်လို့ပြောတယ်
။ခုနကြည့်နေမဟုတ်လား။တိတိပြန်မကြည့်ဘူးခင်ဗျာလို့
မဟုတ်ကြည့်ရောနောက်တစ်ခေါက်ပြောတာဖြတ်ပြီးတော့ပြောတာ
ဒီကအရင်တော့မဟုတ်ဒီကဘယ်လိုလေးလဲဆိုတော့ဗောနော်အဓိကဒီ scale အဲ့ဘယ်လိုလုပ်လဲဆိုတဲ့သဘောတရားကို तू ကအဲ့ဆိုနည်းနည်းမျက်စိတည်းမြင်လာလို့ဗောနော် image တွေပဲဖြစ်ဒါပဲဖြစ်တချို့ဟာလေးတွေပဲဖြစ်ဗောနော်အဲ့ဘယ်လို scale အဲ့လုပ်ကြမလဲအဲ့လိုမျိုးလေးအများကြီးရှိတယ်ဗောနော်အဲ့ဒါနဲ့ပတ်သက်ပြီးမျက်စိတည်းမြင်လာအောင်လို့ तू ကတန်းရှင်းပြရဲဆိုတဲ့သဘောလေးပဲဗောနော်ရိုင်းကောင်းမချုံနေခုချိန်ပါလေနော်ဟုတ်ပါပြီအဲ့လိုဆိုတော့
ဟုတ်ကဲ့
ပြပါမယ်နော်နောက်လည်းမြင်တို့လည်း OpenCV တက်တာမလား surface မှာလည်းတွေ့သလားလို့
ဟုတ်တက်တယ်အဲ့
ဆိုဒီဟာလေးကိုတစ်ချက်နောက်တစ်ထည့်တာနော်ပြီးရင်ပြန်လုပ်လို့ရအောင်ဟုတ်ပြီတခြားလူ question တွေနော်ဒီအားကြတော့ तू က example တစ်ခုပေးတယ်ဗောနောက် example တစ်ခုထပ်ပေးရဒါတွေအကုန်လုံးက R2 ဖြစ်တဲ့အတွက်2 dimension တွေပဲဗောနော်မျက်စိထဲမှာ R3 မဟုတ် तू ပြောနေတာခုနကမားပြီးတစ်လုံးလုံး R2 ပြောတယ်အဲ့ဒါဒါ तू လုံးလုံးနေတဲ့ဟာတွေ R2 မှာပဲဗောနော်ဒီမှာဆိုဒါခုနကအဲ့လို scale နဲ့ reflect လုပ်တယ်အခုက rotate လုပ်မှာသိရမလားခုနကဒါ flip လုပ်တဲ့ process တွေပြီးရင် scale လုပ်တဲ့ process ကိုနှစ်ခုဆို reflection ကိုပြောခြင်းတဲ့ပေါ့ဗောနော်ဒီ operation က rotate ဆိုတဲ့ function OpenCV မှာရှိတယ်အဲ့ဒါကိုလုပ်တာဘယ်လိုလုပ်လဲဆိုတော့မျက်စိထဲမြင်အောင်လို့နော်ကြည့်အောင်
create a linear transformation that is a rotation transformation through some angle theta. And what it does is it takes any vector in R2 and it maps it to a rotated version of that vector. Or another way of saying it is that the rotation, it's not one of those double R's. The rotation of some vector x is going to be equal to a counterclockwise theta degree rotation of x. So this is what we want to construct using our new linear transformation tools. And just to make sure that we can actually even do this, we need to make sure there's an actual linear transformation. I'll just do that visually, because I actually don't even have a mathematical definition for this yet. This is about as good as I've given you. So let me just draw some really fast axes right here. I have to draw them a little bit neater than that. So that's my vertical axes, that's my horizontal axes. I could call this, I'll call this one the x1, and I'll call this the x2 axis. In the last video, I called them the x and the y, but you know, this is the first component of our vectors. This is our second component of our vectors. And so if I have some vector x, like that, we know that a rotation of this, a counterclockwise rotation of this, will look like this. I'll do the rotations in blue. It will look like this, where this angle right here is theta. So this right here is the rotation for an angle of theta of x. That's what this vector right here is. So what do we have to do to make sure that this is a linear combination? We have to show two things. We have to show that the transformation, so the rotation through theta of the sum of two vectors, it's equivalent to the sum of each of their individual rotations. The rotation of the vector x plus the rotation of the vector y. And I'll just show that to you visually. This is the vector x. Let's say that the vector y looks something like, I'll draw both of the original vectors in yellow. So let's say the vector y looks like that. So that's y. So what's x plus y? So let's put heads to tails. If we just shift y up here, if you just shift y up there, that's also vector y, not drawn in standard position. But x plus y would then, well, it would look pretty close to this. Okay, I'm not drawing it. Let me draw it a little bit neater. X plus y would look like that. That would be the vector x plus y. And what would its rotation look like through an angle of theta? What's rotation if you just rotate this guy through an angle of theta? I'm just approximating. It would look something like this. It would look something like that. So,
oh, sorry. Let's touch me, God. Sorry, now.
So this right here, this would be the rotation through an angle of theta of x plus y. Now let's see if that's the same thing as if we rotate x and rotate y and then add them together. So what's y if we rotate it through an angle of theta? If we rotate y through an angle of theta, it's going to look something like, this is all approximation. I should be doing it with a ruler and a protractor. Maybe it looks something like this. And the rotation, so this is right here, that's the rotation of y through an angle of theta. Right there, that's the same theta that I've been doing the whole time. Let me make it in a color that you can actually see. So that's that vector right there. The rotation of x was right there. So if we add the rotation of x plus the rotation of y, I'm kind of fudging it a little bit, but I think you get the idea. You actually get, so this is the rotation of x plus the rotation of y, rotation of our vector y, you actually get the rotation of x plus y. So at least visually, it satisfied that first condition. Now the second condition that we need for this to be a valid linear transformation is that the rotation through an angle of theta of a scaled up version of a vector, it should be equal to a scaled up version of the rotated vector. And I'll just do another visual example here. So let's say this is my vertical axis. Say that this is vector x. Now let's draw a scaled up version of it. So a scaled up version of x, maybe just like x, but it gets scaled up a little bit. So it goes all the way out here. So this is my c times x, and now we're going to rotate that through an angle of theta. So if we rotate that through an angle of theta, you get a vector that looks something like this, rotating it counterclockwise. So this vector right here is the rotation by an angle of theta counterclockwise of cx. That's what this is right there. Now what happens if we take the rotation of x first? So if we just rotate x first, we're going to get this vector right here. So this right here is just the rotation for an angle of theta of x, and then we scale it up. Well, we see it's the same thing. If this scaled up to that when you multiply it by c, then this thing is going to scale up to that when you multiply it by c. So at least visually, I've shown you that this is satisfied. So rotation definitely is a linear transformation, at least the way I've shown you. Now, let's actually construct a mathematical definition for it. Let's actually construct a matrix that will perform the transformation. So I'm saying that my rotation transformation from R2 to R2 of some vector x can be defined as some 2 by 2 matrix. It's 2 by 2 because it's a mapping from R2 to R2 times any vector x. And I'm saying I can do this because I've at least shown you visually that it is indeed a linear transformation. And how do I find A? Well, I start with, since this was mapping from R2, I start with the identity matrix in R2, which is 1, 0, 0, 1. Its columns are the basis vectors for R2, right? We refer this one as E1 and this column vector as E2. And to figure out A, we essentially just perform the transformation on each of these columns. So let me write that. So A, our matrix A is going to be, the first column of it is going to be our rotation transformation performed on the vector 1, 0. And our second column is going to be the rotation transformation, there's a little data here that I'm forgetting to write, times the second column vector, times, or the transformation of that one, 0, 1. This is what our A is going to look like. So how do we figure out what these are? I'm trying to get to some numbers, and this doesn't get me there. So let's try to do that. So let me draw some more axes here. Let me pick a different color. I'll do it in gray. So that is my vertical axis. That is my horizontal axis. I could call this the x1 axis, and this is the x2 axis. Now, this basis vector, E1, what does it look like? Well, it's 1 in the horizontal, x1 is 1 and x2 is 0. So if this is 1 out here, E1 will look like that. Let me do it in a more vibrant color. E1 will look like that right there. Now, if I'm rotating, let me write what E2 looks like. E2 would look like, I'll do it in yellow. E2 would look like this right here. E2. That's that vector, 0, 1. This is 1 in our x2 direction. Now, if I rotate E1 by an angle theta, what will it look like? So if I rotate E1 an angle theta, I'll do it in this color right here. It will still have a length of 1, but it'll be rotated like that. And that angle right there is theta. So this right here is the rotation of E1 by theta. These are all vectors, of course. That's what that is. Now, what are the coordinates for this, or how do we specify this new vector? How do we specify this new vector? Well, we can break out a little bit of our trigonometry. Its new x1 coordinate, we could call it, or its x1 entry, is going to be this length right here. It's going to be this length right here. So if we draw a right triangle, it is the side that is adjacent to theta. This side is the hypotenuse, which is length 1. And so how do we figure out this side? If we call this side the adjacent side over the hypotenuse, let me write it over here. Adjacent over the hypotenuse, which is just 1, is equal to the cosine of theta. Cosine of theta. That comes from SOHCAHTOA. Ka. Let me write that. Ka. Cosine is adjacent over hypotenuse. Adjacent over hypotenuse. And the adjacent side is going to be our new x1 coordinate, right? Well, we can Now, obviously, ignore that 1. A divided by 1 is equal to cosine theta, which means that A is equal to cosine theta, which means that this length of our rotated vector is equal to cosine theta. Its horizontal component, or its horizontal coordinate, is equal to cosine of theta. Now, if we take, what's its vertical component going to be? What's its vertical component? Well, its vertical component is going to be this height right here. It's going to be that height right there, which is the same thing as that height right there. Or we could say sine of theta, and we call this the opposite. Sine of theta is equal to the opposite over 1. So this is going to be equal to sine of theta, right? This over 1, which is just this, is equal to sine of theta from SOHCAHTOA. SOHCAHTOA. So this vertical component is equal to sine of theta. So the new rotated basis vector can be written as cosine of theta for its x component, or for its horizontal component, and sine of theta for its vertical component. This is the new rotated basis vector. Now what about E2? Well, we could do something very similar there. E2 is going to end up looking like this when you rotate it by an angle of theta. It's going to look like that. That angle right there is theta. We can create a little right triangle right there. And so if we want to know its x-coordinate, so now we're concerned with the rotation through an angle of theta of E2, which is that right there, of E2. This is E2 right there. This is going to be equal to what? Its new x-coordinate, or its first entry in this vector, if we wanted to draw it in standard position, or the point that it is specifying, is going to be equal to this distance, which is equal to this distance on this triangle, but the coordinate is going to be the negative of this, right? If this is the distance of 2, this coordinate is going to be minus 2. So what's this? We have an angle. It's a right triangle. This is opposite to the angle. Opposite over 1, opposite over hypotenuse is equal to cosine of theta. So this opposite side is equal to the cosine of theta. So the x-coordinate right here, oh, sorry, my trigonometry is messing up. This is the opposite side. SOHCAHTOA, sine is equal to opposite. Let me write it, because sine of theta is equal to opposite over hypotenuse. So the sine of theta, sine of this angle, is equal to this opposite over the hypotenuse. The hypotenuse is 1, has length 1, because these are the standard basis vectors. So this is equal to the sine of theta. Now, this distance is equal to the sine of theta, but it's going in the negative direction. So it's going to be equal to the minus sine of theta. And then what's its new y component going to be of this rotated version of E2? Well, we just look right here. We have our angle. This is adjacent to the angle. This adjacent side over the hypotenuse, so adjacent over 1, which is just this adjacent right here, is just going to be equal to cosine of theta. So its new y coordinate is going to be cosine of theta. So when we apply the transformation to each of our basis vectors, we get A is equal to the transformation applied to E1, which is cosine of theta and sine of theta, and the transformation applied to E2, which is minus sine of theta times the cosine of theta. So now this is a big result. We've now been able to mathematically specify our rotation transformation using a matrix. So we can now say that the rotation transformation, and it's a transformation from R2 to R2, it's a function. We can say that the rotation through an angle of theta of any vector x in our domain is equal to the matrix cosine of theta, sine of theta, minus sine of theta, cosine of theta, times your vector in your domain, times x1 and x2. And you might be saying, oh, Sal, we did all this work, and that's kind of neat, but how do I apply this? I still have all these cosines of thetas and sines of thetas there. How do I do it? Well, what you do is you pick an angle you want to rotate to and just evaluate these, and you'll just have a normal matrix with numbers in it. So let's say that we wanted to rotate through an angle of 45 degrees, some vector. Well, this is going to be equal to what? We just apply, or we evaluate each of these ratios at 45 degrees. A cosine of 45 degrees is square root of 2 over 2. Sine of 45 degrees is square root of 2 over 2. Sine of 45 is square root of 2 of 2. We have a minus there, so minus square root of 2 over 2. And then times, then cosine is just another square root of 2 over 2. So, and we multiply it times our vector x. So this matrix, if we multiply it times any vector x, literally, so if we have some coordinates right here, and let's say that I were to, I don't know, let's say I were to have a bunch of vectors that specify some square here. Let me see if I can do it properly. Or maybe it has some triangle here. Maybe that'll be a little easier for me to draw. I'll do a square. Let's say it has some square here. Let's say I have some square here in my domain. So this is in R2. Now when I apply, if I literally multiply this times each of the basis vectors, or actually all of the vectors that specify this set here, I will get, when I transform it, I'll get a rotated version of this by 45 degrees. Just to draw it, I'll actually draw a little 45-degree angle right there. And then it will map it to this image right there, which is a pretty neat result. And you can all already, if you ever attempted to write any computer game that involves marbles or pinballs going around, this is a very useful thing to know of how do you rotate things, how do you, and in the future we'll talk about other types of transformations, but this is a super useful one. This is super hard to do, and I remember the first time I wrote a computer program that tried to do this type of thing, I just did it by hand. But when you have this tool at your disposal, all you have to do is evaluate this matrix at the angle you want to rotate it by, and then multiply it times your position vectors. And so, obviously you have a bunch of position vectors here, but here you can just do it times the vertices, and then you can say, okay, and everything else is just connect the dots between them, and then you have your rotated image. And just to be clear, these are the points specified by a set of vectors. And I always want to make this clear, right? This point right here is specified by some position vector that looks like that. When you apply the rotation on 45 degrees of that vector, this vector then looks like this. And the vector that specified this corner right here, I'm doing a different color, that specified this corner right here when you rotate it by 45 degrees, then becomes this vector. And the vector that specified that corner over there, that now becomes this vector. That's what's actually being mapped or actually being transformed. Anyway, hopefully you found this pretty neat. I thought this was at least for me, this is kind of the first really neat transformation. And you can already start thinking about how to extend this into multiple dimensions, especially three-dimensional. So if you ever try to actually do it by hand, three-dimensional rotation becomes very confusing. But in the next video, we'll actually figure out a way to do three-dimensional rotations around certain axes.
ဟုတ်ပါပြီဒီဟာလေးကအမှန်မှန်တော့ဗောနော်လဲဆိုတာဟိုပထမတော့ကနေ sin တို့ cosine တို့ကြာ rotation နဲ့ပတ်သက်တာတည်တာတော့သိရမှာ orthogonal အဲ့လိုတယ်မလားကိုရီးအဲ့လိုပြဿနာတက်တာ orthogonal ဖြစ်တဲ့ဟာကိုသိရမလားဘယ်လို 90 degree ဖြစ် orthogonal ဖြစ်တာတို့ sin တို့ cosine တို့အဲ့ဒါနဲ့ပတ်သက်ပြီးပြောတော့ဟုတ်တယ်ဟုတ်အဲ့နဲ့ပတ်သက်ပြီးလည်းဆိုနည်းပြောထားပါလားအမှန်ဆိုဒီလို operation တွေသူလုပ်တယ်ဆိုရင်ကျွန်တော်မျက်စိနဲ့မြင်လာစေချင်တယ်မဟုတ် rotation လုပ်တယ်ဆိုတာ degree နဲ့ပါတယ်ပေါ့နော် degree နဲ့ပတ်သက်ပြီးလို့လုပ်သွားတယ်ဆိုရင်ပေါ်လေးကိုမျက်စိနဲ့မြင်လာစေချင်ပါတယ်အဲ့ဒီဟာနည်းနည်းတော့ခေါင်းစားတဲ့ဟာမျိုးဆိုရင်အရင်ကလည်းဦးစားမပေးချင်ဘူးဒီကသဘောတရားလေးကိုပဲပေါ့နော်သူကဒီလိုလုပ်ပါလားဆိုတာလေးကိုမြင်စေချင်တော့တာပါပဲထွေထူးတော့မဟုတ်ဒီလိုနည်းနည်းမေးကြည့်နေတာရှိရတယ်ဆို
Transformation applied to E1 which is
အဲ့ဒါဆိုမေးကြရရှိရဒီဟာလေးနဲ့ပတ်သက်ပြီးတော့လေခေါင်းရှုပ်နေနဲ့ခဏထားမှာသူ formula လေးနည်းနည်းများဖြစ်တယ် cosine တို့ sin တို့ဒီ cosine အဲ့ဒါတွေကလည်းဆိုလို့10တန်းမှာသင်ခဲ့ရတဲ့ဟာတွေဖြစ်တဲ့အတွက်ပေါ့နော်တချို့ဟာလေးတွေပြန်ပြီးမှတ်မိကောင်းမှတ်မိနိုင်ရှိတယ်သူ့မှာ formula လေးရှိပါတယ် cosine 90 degree ဆိုဘယ်လောက်ရဖြစ်ပါတယ်လို့ 1 ဆိုရင်ဘယ်လောက်ဖြစ်ပါဒီ formula လေးတွေရှိပါတယ်လားဟုတ်တယ်ဟုတ်အဲ့လိုဆိုတော့ဒီဟာလေးအဲ့ဒီဟာလေးသုံးသွားတာပေါ့နော်အရင်ထွေထူးတော့မဟုတ်ဆိုတော့အရင်ကောင်းမရှုံးနေ okay anything my father called me okay never mind နောက်တစ်ခုသွားအောင်နော်အားလုံးအဆင်ပြေကြလားအတိုင်းလေးလုပ်ပါအောင်တစ်ချက်ကြည့်မယ်နောက်အတိုင်းလုပ်ပါအောင်အဆင်ပြေကြလားလို့ဒီဟာလေးကိုဒီအဲ့ဒါဆို 3D ကိုလုပ်တယ်ပေါ့နော်ခဏလေးလက်စားဒီ 3D ကိုခဏလေးနော်ဘယ်လောက်ကြာလဲကြည့်မယ်12မိနစ်ဆိုတော့12မိနစ်ပြအောင်လုပ်လိုက်မယ်ဆိုတော့ဒီဟာပြင်လဲဆိုခဏရ rotation ကိုပြည့်ရနော် rotation ကိုပြည့်နောက်တစ်ပတ်ကြာနေဟာကျွန်တော် rotation ကိုဒီဟာလေးတစ်ခုပြအောင်လုပ်လိုက်မယ်နော်အခုန R2 မှာလည်းဆိုလုပ်နေရပါဘောနော်အခု R3 ကိုသွားမယ်အော် R2 မှာခုနလုပ်နေရအခု R3 ကိုသွားမယ်ပေါ့နော်အဲ့လိုဆိုဘယ်လို
last video
ဘယ်လို rotate လုပ်လဲပေါ့နော် R3 မှာ R2 မှာကျတော့ကိုရီးယား familiar ဖြစ်နေတဲ့လူတွေပေါ့နော် R2 ကတိတ်ပြီးတော့ကိုယ့်အတွက် trade through မဟုတ်ဒါပေမဲ့ R3 ကကျတော့နည်း visualization နည်းနည်းလုပ်ရမှာဆိုကြည့်အောင်နော်3 dimension ဆိုတော့လीနော်
we defined a transformation that rotated any vector in R2 and just gave us another rotated version of that vector in R2. In this video, I'm essentially going to extend this, but I'm going to do it in R3. So I'm going to define a rotation transformation. Maybe I'll call it rotation, well, I'll still call it theta, but it's going to be a mapping this time from R3 to R3. And as you can imagine, the idea of a rotation and angle becomes a little bit more complicated when we're dealing in 3 dimensions. So in this case, we're going to rotate around the x-axis. So let me call it. So this is going to rotate around the x-axis. And what you see, what we do in this video, you can then just generalize that to other axes. And if you want to rotate around the x-axis and then the y-axis and then the z-axis by different amounts, different angles, you can just apply the transformations one after another. And we're going to cover that in a lot more detail in a future video. But this should kind of give you the tools to show you that this idea that we learned in the previous video is actually generalizable to multiple dimensions, especially 3 dimensions. So let me just be clear what we're going to be doing here. So let me draw some axes. So that's my x-axis, that is my y-axis, and this is my z-axis. And what I'm saying is of course this is R3, but any vector here in R3, I will be rotating it counterclockwise around the x-axis. So we'll be rotating like that. So if I had a vector, and I'm just drawing it in the zy plane because it's a little bit easier to visualize, but if I have a vector sitting here in the zy plane, it will still stay in the zy plane, but it'll be rotated counterclockwise by an angle of theta, just like that. Now, a little harder to visualize is a vector that doesn't just sit in the zy plane. Maybe we have some vector that has some x component that comes out like that, and some y component, and then some z component that looks like that. Then when you rotate it, its z and its y components will change, but its x component will stay the same. So then it might look something like this. Let me see if I can give it justice. So then the vector, when I rotate it around, might look something like that. Anyway, I don't know if I'm giving it proper justice, but this was rotated around the x-axis. And I think you understand what that means. But just based on the last video, we want to build a transformation. We want to make this, let me call this rotation 3 theta, or let me call it 3 rotation theta, to know that we're dealing in R3. And what we want to do is we want to find some matrix, so I can write my 3 rotation sub theta transformation of x as being some matrix A times the vector x. And since this is a transformation from R3 to R3, this is of course going to be a 3 by 3 matrix. Now in the last video, we learned that to figure this out, you just have to apply the transformation essentially to the identity matrix. So what we do is we start off with the identity matrix in R3, which is just going to be a 3 by 3. Let me draw it like, you're going to have 1, 1, 1, 0, 0, 0, 0, 0, 0. Each of these columns are the basis vectors for R3. That's E1, E2, E3. I'm writing that probably too small for you to see, but each of these are the basis vectors for R3, and what we need to do is just apply the transformation to each of these basis vectors in R3. So our matrix A will look like this. Our matrix A is going to be a 3 by 3 matrix, where the first column is going to be our transformation, 3 rotation sub theta, applied to that column vector right there, 1, 0, 0. And then I'm going to apply it to this middle column vector right here. So I'm going to apply it, well, you get the idea. I don't want to write that whole thing again. I'm going to apply 3 rotation sub theta to 0, 1, 0. And then I'm going to apply it, I'll do it here, 3 rotation sub theta. I'm going to apply it to this last column vector. So 0, 0, 1. We've seen this multiple times. So let's apply it. Let's rotate each of these basis vectors, the basis vectors for R3, let's rotate them around the x-axis. So the first guy, if I were to draw it in R3, what does he look like? He only has directionality in the x direction, right? If we call this the x dimension, if this if the first entry it corresponds to our x dimension, the second entry corresponds to our y dimension, and the third entry corresponds to our z dimension, then this guy only, this vector would just be a unit vector that just comes out like that, right? So if I'm going to rotate this vector around the x-axis, what's going to happen to it? Well, nothing. I'm just going to, I mean, it is the x-axis, so when you rotate it, it's not changing its direction or its magnitude or anything. So this vector right here is just going to be the vector 1, 0, 0. Nothing happens when you rotate it. Now, these are a little bit more interesting. To do these, let me just draw my z-y axis. Let me just draw my z. So that's my z-axis. And this is my y-axis right here. Now, this basis vector, it just goes in the y direction by 1. So this basis vector just looks like that. And it just goes, it has a length of 1. And then when you rotate it around the x-axis, when I draw it like this, you could imagine the x-axis is just popping out of your computer screen. So I could draw it, like this is like the tip of the arrow, it's just popping out. Instead of drawing it at an angle like this, I'm drawing it straight out of the computer screen. So if you were to rotate this vector right here, this blue vector right here, this vector right here, by an angle of theta, it'll look like this. It'll look like that. And we've done this in the previous video. What are its new coordinates? Well, first of all, will its x-coordinate have changed at all? Its x-coordinate was 0 before because it doesn't break out into the x dimension. It just stays along the zy plane. It was 0 before. When you rotate it, it's still on the zy plane. So its x direction, or its x component, won't change at all. So the x direction is still going to be 0. And then what's its new y direction? Well, here we do exactly what we did in the last video. We figure out this is going to be its new, I guess I don't want to draw a vector there necessarily, but this length right here is going to be its new y component, and this length right here is going to be its new z component. So what's its new y component? So this is going to be, and we did this in the last video, so I won't go into as much detail. But what is cosine of theta? The length of this vector is 1, right? These are the standard basis vectors, and one of the things that makes them a nice standard basis vector is that their lengths are 1. So we know that the cosine of this angle is equal to the adjacent side over the hypotenuse. The adjacent side is this right here, and what is the hypotenuse? It's equal to 1. So this adjacent side, which we said is going to be our new second component, or our second entry, is going to be equal to cosine of theta, right? That's A. You can just ignore the ones. It's going to be equal to cosine of theta. And what's going to be its new z component? Well, sine of theta is equal to the opposite side, this side, over 1. So it just equals this opposite side. And the length of that opposite side is this vector's, once it's rotated, is its new z component. So that you get a sine theta right there. Now we just have to do everything in the z direction. So this z basis vector right there, what does it look like on this graph? Let me just actually redraw it just to make things a little bit cleaner. So that's my z-axis, and this is my y-axis. And my z basis vector, E3, starts off looking something like that. E3 looks like that. It just goes only in the z direction. So first of all, let's just rotate it by an angle of theta. So I'm going to rotate it like that. That's an angle of theta. So what's its former x entry was 0. It did not break out in the x direction at all. And of course, we're still just in the zy plane, so it won't be moving out in the x direction still. So it's still going to be a 0 up here. Now what about its new y component? Its new y coordinate, I guess we can call it, is going to be this length. There's going to be this coordinate right here. And how can we figure that out? Well, that length is the same thing as that length. And if we call this the opposite side of the angle, we know that the sine of theta is equal to this opposite side over the length of this vector, which is just 1. So it's just equal to the opposite side. So the opposite side is equal to sine of theta, but our new coordinate is to the left of the z-axis. So it's going to be a negative version. We did this in the last video. So it's going to be a negative sine of theta. So this is going to be negative sine of theta. This point right here, that coordinate. So it's minus sine of theta. minus sine of theta. And then finally, what's its new z coordinate going to be? That's going to be this length right here. And we know that this length, if we call that adjacent, we know that the cosine of our theta is equal to this divided by 1. So it's equal to that adjacent side. So we can just put a cosine of theta right there. And we get our transformation matrix. We're done. Our transformation matrix A is this. So we can now say our new transformation that this video is about, my 3, I call it a 3 because it's a rotation in R3, but it's around, maybe I should call it 3 sub x because it's a rotation around the x-axis, but I think you get the idea. It is equal to this matrix right up here. Maybe I could rewrite it, or, well, actually, let me do it this way. Let me delete all of this. So I don't have to rewrite. So my transformation that this video is about, the 3 rotation theta of x, that transformation is equal to this matrix times whatever vector x I have in R3. And you might say, hey, Sal, that looks exactly like what you did in the second. If you remember the last video when we defined our rotation in R2, we had a transformation matrix that looked very similar to this. And that makes sense because we're essentially just rotating things counterclockwise in the zy plane. Now you might say, hey, Sal, why is this even useful? You extended it to 3 dimensions or to R3. I saw what you did in R2. Why is this useful? It's kind of a limited case where you're just rotating around the x-axis. And I did for 2 reasons. One, to show you that you can generalize to R3. But the other thing is, if you think about it, a lot of the rotations that you might want to do in R3 can be described by a rotation around the x-axis first, which we did in this video, then by rotation around the y-axis, and then maybe some rotation around the z-axis. So you can actually define, this is just the special case. This is just a special case where we're dealing with the x-axis, rotation around the x-axis, but you could do the exact same process to define transformation matrices for rotations around the y-axis or the z-axis, and then you can apply them one after another, and we'll talk a lot about that in the future when we start applying one transformation after the other. But anyway, hopefully you found this slightly useful. It's a slight extension of what we did in R2.
ဟုတ်ပါပြီဒီကခေါင်းနဲ့ချုပ်တယ်ဆိုတော့လည်းတခြားကိစ္စလုပ်မယ်ပေါ့နော်ဒါလေးကခေါင်းနဲ့ချုပ်တဲ့ topic တွေမှန်တော့ဗာလဲဆိုတော့သူကဒီခုနကလည်းဆို R2 ကလောက်သွားတဲ့ operation R3 မှာသူကဘယ်လိုပြန်လုပ်သွားလဲဆိုတော့နော်ခုန sin နဲ့ cosine နဲ့ပတ်သက်တာသူပြန်လုပ်သွားပါတယ်ဆိုတော့လေနော်ဟုတ်ပါပြီဒီကလည်းရဲခေါင်းမချုပ်တယ်အဲ့ဒါဆိုတနေ့ကြည့်တော့ခေါင်းချုပ်တယ်ဆိုရင်လည်းတခြားလုပ်လဲပေါ့နော်ဒါပေမဲ့အဓိကသူ့ရဲ့အဓိကသဘောတရားလဲဆိုတော့ဒီမှာပြောချင်တဲ့သဘောတရားပေါ့နော်ဘာကြောင့်အဲ့လိုလုပ်နေလဲဆိုတဲ့သဘောတရားလေးပေါ့နော်သူက R2 မှာတော့လည်း transformation လုပ်တော့ဘယ်လိုလုပ်သွားလဲဒီကသိထားမိလားမသိဘူး transformation လုပ်တိုင်းလည်းဆို utilize လုပ်နေတာပါ identity metric ကို utilize လုပ်နေတာเนาะသိထားမိလားဒီမှာဆိုလည်းကြည့်ဆိုတော့ R2 မှာတော့လည်း R2 ရဲ့ဒီ transformation metric လုပ်တော့လည်းအဲ့ဒါဆိုတော့ identity metric ကိုယူသွားတယ် R2 ရဲ့ identity metric ဟုတ်တယ်ဟုတ်အဲ့ဒီ same time မှာတူတူပဲပေါ့နော် R3 မှာလည်းသူ identity metric ကိုသုံးပြီးတော့ transform လုပ်သွားတယ်ဆိုတာလေအုံနောက်တဲ့ message နေတယ်ပေါ့နော်အဲ့ဒီပုံစံမျိုးပြီးရင်ဒီ cos တွေ cosine တွေအတိုင်းဖြစ်နေယူရမယ့်ဟာမျိုးလေးပေါ့နော်သူကကိုယ့်ရဲ့ angle degree ဘယ်လိုရှုရမလဲပါမယ်ဆိုဒီလိုမျိုး formula နဲ့သုံးပါတယ်ဆိုတဲ့ဟာလေးရှိရပေါ့နော်အဲ့ဒါလေးတစ်ချက်အုံနောက်တဲ့ message တွေမှာလေလို့နော် okay any question for today Okay မရှိရင်အဲ့ဒါဆိုဒီမှာပဲအံ့မယ်လေအားလုံး okay ဟုတ်အတန်းလေးပြန်လုပ်ကြမယ်ကဲပါ
ကြည့်နိုင်ပါ
ကဲပါ okay အဲ့ဒါနဲ့ပြန်တွေ့ကြမယ်နော်အားလုံး bye bye ပါခဏနားလိုက်နော်